Okay. Thank you. Both this front group. Everyone needs your lab books and your periodic table out. And then one other thing. Do you remember what it was? A good attitude. Thank you, new man. All right. You need a lab book, correct? Okay. Today is one of my very favorite days of all of chemistry. We're talking about valence electrons. Now, some of you have learned this stuff in Bert's class before. I'm aware of that. I'm proud that Bert took everything that I taught him and has given it to you. All right, it's okay. Yeah, we have talked about this before as well. So good job. All right, today's goals, and we may not get this far. We may get farther. I don't know. But today's goals are two things. And I know you're like, wait a minute. So far, we've only learned one thing a day. You can barely do that, right? So it is good. Here we go. Let's just quickly review. You're like, not again. Yeah, again. Eat it. Okay, here we go. This, tell me, you're going to point up or down. Where should the arrow point? Down, down, and down. Lower and lefter. And that only applies to who? Metals. You guys are awesome. Okay, our nons, I'm just going to call them nons for right now. Okay, Meg says this way and this way, higher and righter. And I should not include family 8, right? Tell your buddies why I wouldn't count family 8. Because it's weird. Okay, we good? The family 8 is called the noble gases because they don't mix with other things. All right, when you get way down low, they actually do form some really crazy things. But in this class, we're generally going to say they don't do anything. Okay with that? So this is really it. Like, we've got this. Lower lefter, higher righter. Never forget it or I'll be offended. Are we clear? I will hate you. Just kidding. I don't hate, but I hold grudges for decades. This John Rasmussen. Okay, here we go. Turn the page. Claire, this is beautiful. It's all filled in and nice. Turn to page 4 if you would. I've never been more proud of you. Actually, I have. Finishing a 4 with a massive migraine. I was pretty proud of you. Okay, the top of page 4, we should have already done. That's where we put arrows and we put like HWA, CHWA, all that stuff. Does that sound familiar? Thumbs up if that sounds familiar. We've done it. Just trust me, we did it. All right, the conclusion questions. Are we ready? There's 4 conclusion questions in the middle of page 4. 4 on 4. Would you look at those real quick and try to answer them on your own? Micah, try and answer them on your own for the next 2 minutes. And ready, set, go. Hey Siri, set a 2-minute timer. Hey Siri, set a 2-minute timer.
2 minutes, starting now.
Should have started 2 minutes ago. If you don't know the answers, you can ask your partner. She's very smart. What did this one do to deserve not having paint on it? No. Oh, okay. How's the back today? All right, good. I was lifting yesterday.
Usually good.
Was it good? All right,
I'm
good.
excited for today because I've never been lifting.
Well, don't look at me. I don't coach javelin. I will never throw the javelin again based on my shoulder's condition now. It's gone. Okay. Here we go. We closer? We closer? You're looking great today, child. Yep. And everyone else too. What? Okay, well, the timer says the timer shut off.
Oh, looks like we need more time.
How did it
Wait,
shut?
there's satellite on. How do you spell
How has it shut off?
Probably because you didn't have enough service, so she just didn't do it. Wait,
Yeah, it started and it started counting down. You heard it. Who heard it? I heard it. Okay, well, you have time until I get back with my drink. Yes.
How do you spell Florida?
FLU. Oh.
No, it's not.
Oh, somehow my timer, which wasn't showing up, tells me we're done.
Why are you always up there?
On my phone.
All right. Someone in Miller's room just said hi, and I have no idea who they are. It's okay though. Happens all the time. Okay. Here we go. We had 4 questions. Number 1. Hold on. Number 1 said, what does the heavy staircase? Metals and nonmetals. Nailed it, right? Who had that? I feel like you had that first day here. Who'd you have for A? Who taught you chemistry A? Didn't you? Teach Goddard. Or did you take it last year? Okay, never mind. I'm like, hey, Durant, worst teacher ever, doesn't even know her kids. Just kidding. Okay, staircase does that. Next, why shouldn't the reactivity include family 8? We just said it because they are the noble gases. Their valence electrons are full, which we'll learn about in a minute. Next, number 3, based on that, which would be more reactive, Na or Mg? So wait, hold on. Oh, would Mg or Na react more vigorously in cold water? Nah. And Mg or Be, whatever, it's Mg. That was really weird. You're right, Roach. It was written weird. What is the most reactive, oxygen or fluorine? Fluorine, all day, every day. Okay, fair enough. Tayson, you got them? Okay. All right. Today, some notes. I literally think that this is like when chemistry finally makes sense. Personally, for some of you, it won't ever make sense, but we can still be friends. Basketball players said they'd come in, but they're not, making me sad. All right, here we go. Feel like we did that. Where are you? Where are you? Okay, here we go. You ready? Anyone ever heard the word vagrant? It's not big. What is it? Okay, you've heard it. Okay, no one? Yeah, oh, sorry. Yep. What? It doesn't have a home. Someone knows this vagrant term. Vagrant, that's like in the news, they'll be like, a group of vagrants were arrested or whatever for sleeping under the train tracks. Whatever. It means it's homeless. They move where they want. They're nomadic. Perfect. So vagrant, valence electrons. We've talked about them before. They are the electrons in the outermost. Does that sound familiar? Okay, we have core electrons, and those are the ones in the middle of the atom, and the valence is on the outside. Thumbs up. All right. So vagrant valence electron means that electrons moving on the outside of the atom. Fair enough. Okay, here we go. Valence electrons are the electrons in the highest occupied energy level of an atom. So last try, we did all this business, like 1s2, 2s2, 2p6, 3s1. Sound familiar? Okay, 3s1. 3 means it's in the third row. So look over there. It's in the third row. S means it's on the left side, and 1 means it's 1 over. So what atom are we talking about? Na. Who said Na? It was a boy. Not you. Oh, right here. Sorry. It's like Whitaker doesn't know anything, but he said it. All right. It's just kidding. What?
Live. Whitaker does know stuff.
First one ever. Just kidding. Okay, I shouldn't pick on you. I just
At least he probably knows how to spell fluorine. When
spell
it's like
fluorine. Most people
right.
spell it wrong.
Fluorine.
Don't look.
F-L-U-O.
Never mind. He got it. Everyone goes, oh, you. But moving on. Okay, here we go. This is the first atom in the third row. That's all. We're talking about Na. When we talk about valence electrons, I guess that way for you guys. When we talk about valence electrons, we're talking about the ones on the outside. Everything in the third row. That's all. They're the ones that are involved in chemical reactions. So those are the ones we care about. Okay, next. Remember dot structures? Dots were easy, I hope. All right, we had Mg. Magnesium. Thank you. All right, Mg had 2 dots. There's a complicated reason why, and then there's an extremely easy reason why. Why does it have 2 dots? Because it's in the second family. Perfect. So when you look at the periodic table and you have like 1, 2, 3, 4, 5, 8, those numbers tell you the number of dots, and it also tells you now the number of valence electrons. The yeah. So in this class, we do what we call the representative elements, and those are family 1 and 2. And then the D, we just kind of ignore in this class. And then we come over here and it's 3, 4, 5, 6, 7, and 8. So this periodic table does not show it as the representative elements. And I don't know why they call them that, but the representative elements means the S's and the P's. Okay, so that's why if you look here, and if you want, like, you don't have to, but you can put a 1, 2, 3, 4, 5, 6, 7, 8 for valence electrons. You can put it on the top, 1, 2, 3, 4, 5, 6, 7, 8. You're going to put charges up here in a little bit too. You can put it down here, or you can be like, hey, dots, there's 1 dot in family 1 because it has 1 what? Valence electron. Does anyone remember the blue page at the start of today? We had 2 goals. 2 goals. Do you remember what the first one was? Should I go back in time? Oh, wow, that was a long time ago. What's the first goal? There you go. Determine the number of valence electrons in an atom. We'll pop quiz. Here we go. I would like to know why my throat just died. It's all that chlorine from yesterday. All right, are we ready? I want to know the number of valence electrons in the following atoms. We'll just make this one easy. So Na, how about Br? How about, I don't know, Sb? Let's go Al, and we'll make it an even 5, which doesn't make sense because that's an odd number, but whatever. Okay, will you look at your periodic table and determine the number of valence electrons on these atoms real fast? Write them somewhere on that instead of playing with your phones. Yeah, it was. Oh. All right, so they're just hair ties. I usually go 2. They're getting brittle. I can feel them. Yeah, they're getting pretty brittle. They're like 5 years old. That's all you do. But yep. The best Walmart has. Okay. How we doing? Got a thumbs up? I got a there it is. Why would I leave it over here? Okay. Raise your hands if you're done with all 5 of those. You're just telling me how many valence electrons are there. In the last lab book, we had a test on electron dots. And like we taught you how to draw them. But ultimately, you can't draw on canvas. So it just said how many dots are in each one. You're like, wow, this is easy. Because dots was equal to family number, right? Valence electrons are dots. Valence electrons are family number. So here we go. Na has how many? 1. Good. Br has how many? 7. Sb? 5. Al? 3. Sr? 2. Raise your hands if you got all 5 of them right. I saw it. It's okay. It is the same thing. So we can still be friends, but like it's getting sketchy though. Yes, Daniel, or are you just telling me you got it right? Okay, good. So easy, easy, easy. So do you feel successful that you have the ability to determine the number of valence electrons in an atom? Okay, I feel like it has been taught successfully. Let's fast forward. Okay. Now, by the way, the reason we care, we're going to learn it here in another slide, but the core electrons, they don't react. The outside ones do. And reactions are determined really by how the electrons are changed. So that's, we're going to get to that slide here in a minute. Whatever, electrons are known as dots, just put dots. And then Grant does it different than me. So we'll go the way all of you learned it. It was like 1, 2, 3, 4, 5. Oh, what am I doing? What? Oh, sorry. 1, 2, 3, 4, 5, 6, 7, 8. Just write it and let's move on with our lives. I start on the right side. That's the only difference. And it doesn't matter. It doesn't matter. Okay. Okay, next. All right. So I have it right here, so I guess I won't erase it. First question, what is the electron dot representation of SI? It's right here, a number right here. Well, this is out of order. I knew it didn't sound right. Where is that slide? It has been deleted, or I skipped it somewhere. Thomas Davidson. It's gone. The most important slide of the second most important slide. Are we ready? Valence, that's the blank. Electrons are the only electrons used in formation of bonds. Bonds, B-O-N-D-S. Sorry. Bombs. So they determine the chemical properties of the element. They go in a bucket or like a can. Hold on. The words are valence, bonds, and chemical. Oh, whoa. Oh, he never showed up. What? Oh, for last try. Yeah. There we go. Thanks, Maren. Okay, are we all right with that sentence? Okay, now what class are we in first off? What is this class called? Chemistry. We care about the chemical reaction or chemical properties. Fair enough? Which means if this whole class is called chemistry, then really this whole class is about valence electrons. The valence electrons determine how things react. Okay, so now the first day of this class, this trimester, we threw lithium into water, right? We all right with that? And a reaction happened. We took sodium and we put it in water and a reaction happened. We put potassium in water and a reaction happened. Well, here's why they react. How many valence electrons do they have? One. All of them have one. So they're going to behave pretty similar. They all, well, I don't know how I hit that twice, but whatever. They all have one valence electron that they don't want. They all want to give it away. So when they do that, hydrogen separates from water and we end up with NaOH, sorry, LiOH. We end up with hydrogen plus NaOH. Any guesses what this will be? Hydrogen and KOH. These all react the same way because they all have one single valence electron. Sort of, okay? Okay, then the next day. All right, we took Mg and we added it to water. And a reaction happened if it was warm. Ca, and we reacted it with water, and a reaction happened even if it was cold water. All right, it turns out that hydrogen's given off. Any guesses what we have here? Ain't no hoes in chemistry, okay? OH. But whoops, that was terrible. What? Okay, what did I do? Okay, oh, I will come over here and look at that screen. That was scary. All right, we have MgOH2. We have H2 plus Ca. Any guesses? OH2. That's hydroxide. We'll learn about it. But here's what I want you to think about. Why versus Why did something in family 1 make LiOH, NaOH, and KOH, but family 2 made MgOH2, CaOH2? Talk, 30 seconds. Ready? Talk to him, not to me. Talk, why? What's the difference? All right, what did you think, Venable? That was a good conversation. Okay, Claire got it. Raise them up, Claire. She said because this one has 2 valence electrons. That's what you said.
Yeah, I know.
Okay, so versus family 1, what did they have? 1 valence electron. Because we can look here, we don't know a ton of chemistry, but we can say, hey, when I put a metal in water, the water's pretty good at this, or the metal's pretty good at whatever, but it's making a 1 metal to 1 hydroxide. Then we come over here. we have a 2 metal to 2 hydroxide because the valence electrons are different. Okay, here we go. Not a hard question. If I were to put aluminum in water, and let's pretend reacted, because it won't, but pretend it did, what do you think it would form? What? There you go. We have hydrogen gas plus AlOH3. Sort of with me? Okay, go ahead. That tells you how many of the things are attached to the thing. So if I were to draw this picture, like KOH, whoops, whoa, I didn't mean to do that. KOH would have a K, an O, and an H. And it would look like that. We'll learn how to do that in a couple of days. The next one though, if it's MgOH2, I would have an Mg, an O, an H, an Mg right here, another O, and an H. It would look like that. So instead of just one OH that hung out with K, Mg needs 2. Okay, we're going to learn this in another 30 seconds. What's that? We're going to learn there won't be any more dots about Mg. I kind of jumped ahead because he asked a great question, but we're not there yet. Okay, but aluminum, I said 3, right? So extend page is not here. Okay, it disappeared again. Al, OH, OH. I don't know why I did it that way. OH. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. It's going to be similar. It's going to react, but it's going to be in a 3-to-1 ratio because aluminum had how many to give? 3. The valence electrons determines how something reacted. Can you tell me which is more reactive, family 3 or family 1? Family 1. It's easier to remove 1 than 3.
So you would need
I didn't
3
get
water
that.
atoms.
Could
Well,
you try
I
again?
didn't even ask you, okay? Sorry, what?
So you would need 3 waters to
I'm
make
not sure I
1.
understand.
Clearly she doesn't. Yes, next lab book, we're going to balance. It's all going to come together, but yeah. All right. And I'm not going to ask if everyone understood your question because it'll blow some of their minds, but it's a great question. Okay, let's get into this. All right, let's just hurry. SI has 4 dots and let's just move on. These are questions at the bottom. Nice, Claire. When Bree is not here,
I do good.
you do better. She may be a distraction in your life. Yeah. Now, there'll be a seating chart eventually where you don't sit by her and you're going to complain. And I'm going to say, remember. Okay, good. Okay, next, electron configuration for the valence electrons of SI. This is how Durant taught them. So it's 3s2, 3p2. If you wrote the whole thing,
I thought you were supposed to do that. SiOH6.
no, don't worry about it. Don't even worry about it. Wow, smart girl. That's not what I was looking for, but that was a great idea.
That's dumb.
It's not dumb. Okay, next, give the electron configuration for just all family 7s. You would have a V, or sorry, an X, then 1, 2, 3, 4, 5, 6, 7. That's all. Okay, now I know I went through the conclusion questions right, but that's because I want to actually get to dessert, which is the next slide. I love the next slide. Well, this one. Yeah, this one. Okay. Are we ready to like hopefully finally understand? Like we've been in chemistry 3.5 months and we're finally going to do chemistry. All right, here we go. First off, Griffiths, you're a fantastic singer. Tell me what an octet is. That's 8 people. It's 8 of whatever I want, right? 8 people. 8 notes, 8 legs, 8 sides on a like, yeah, that would be sick. Octagon, 8 sides, right? So we're solid on that, right? Okay, here we go. Atoms, just as we find them on the periodic table, before they're with anything else, atoms react by changing their valence electrons. I'm going to write a ton on this and talk on this slide for a while. You're welcome to take additional notes instead of complaining. It's the best slide in years. Are we ready? Atoms react by changing the number of their valence electrons so as to acquire the stable electron structure of a noble gas. Okay. Where do the noble gases live? In the 8th column. What's this rule called? The octet. What do atoms want to become like? Family 8. Are you with me? Okay. For the rest of today, I want you to think about the periodic table as the periodic descending cylinder. Can you do that for me? That's what it does. All right. So the reason I want you to think about it this way, weird, because it's really over there. Okay. If you look at the periodic table this way, it will help today because you need to know that family 1 is actually right next to family 8. It's just that way. It's just left 1. You okay with that? Like family 1's here, and then it's that way. You with me? Okay, now, if that didn't make sense, it's fine. We'll move on. But just trust me that family 1 and family 8 are just 1 away. So here we go. Atoms, they will react by changing. And I said this 10 times, but we're now here. They're going to react by changing their valence electrons by doing one of 3 things. Are we ready? There are atoms in this world that will lose valence electrons to become stable like a noble gas. And I know we called something losers yesterday. Metals are losers. Follow me here. So metals react by losing their electrons so to become like a noble gas. You with me? Okay. Now, cylinder again. Metals in family 1 want to become like family 8. So how many do they want to lose? Just 1. If they lose 1, what? Yeah, we'll talk about hydrogen and helium. Make sure I don't forget to, though. All right. So here, all they got to do, kick out an electron, and then they chemically become like family 8. Now, careful. They don't just randomly turn into noble gases. They are still their things. Lithium is still lithium. We just call it a lithium ion. It becomes charged. Okay. So metals lose valence electrons in a chemical reaction. Are we okay with that? Okay. Well, we've learned about opposites in the last couple of days. What do you think takes then, or gains, I should say? Nonmetals. Nonmetals want to become noble gases. The only way they can do it, well, the easiest way they can do it is to do what? Is to steal some. Because look, here's fluorine. We learned it was the sexiest, whatever, winner yesterday, right? It's in family 7, and it's the best looking one in family 7. So if it can get just 1 more electron, it can behave and feel stable like neon. So fluorine's out there trying to steal your girl, which it can. Richer, better looking, taller, better teeth, less acne. All right. Played football instead of run cross country. Just kidding. Nothing's hotter than cross country boys. All right. No. That sounded really unique. But anyway, moving on. Are we ready? Follow me here. There's a new word we're going to say. I said it a minute ago. But when a metal loses an electron, it becomes charged. I want you to think about this just super fast. When a metal loses an electron, it becomes charged. Because let's think of lithium. It has one valence electron, right? If it loses it, it now has no valence electrons. Think about me here, though. Lithium has 3 total electrons. Are you okay with that? It's element 3. All right. So lithium has 3 electrons and 3 protons. We learned that in the last unit, right? In chemistry A. But if it loses one, it now has 2 electrons and 3 protons, which I'll write as a plus sign. Well, 2 minus plus 3 is positive 1 now.
-2 plus 3. Not 2 minus.
Okay, either way, I'm sorry. -2 plus 3 makes it a positive 1. Because when you lose an electron, you now have more protons than you have electrons. Okay? When the metal loses, it becomes charged, and we call it an ion, or a specific name is the cation ion. You know what that is. Why is it called a cation ion? Because it's positive. That was a mom joke. Okay, I didn't say it. Cat and is like a positive and a negative thing in science. Yeah, that's what they call it in YouTube videos from Europe. It becomes a cation. Okay, you're right. And here's my dad joke. A cat ion is positive because it's in the name.
I like that one better.
Yep, the T tells you that's the positive one. All right, you're looking at me weird, but I don't care. It's called a cat ion. Fair enough? All right. Cat in science means positive and means negative, in case you care. Okay, well, you did ask, so you do. All right, so now the non-metal. Let's think about the same thing. Fluorine has 9 electrons and 9 protons. So usually that's neutral, right? But it wants to gain. It wants to gain. So this number goes to 10. 10 negative, sorry, negative 10 plus 9 now equals what? Negative 1. So when a nonmetal gains, it becomes negative, and we have a name for that. It's called an anion. An anion. Fair enough? Or, look at me, I'm losing some of you. That makes me sad because I just love this stuff. Or, just quick, when a metal loses and a nonmetal gains, I form 2 ions. Are you okay with that? This process has to happen together. A metal can't lose unless a nonmetal is there to take, and a nonmetal can't take unless a metal is there to lose. When the process of losing and gaining happens between a metal and a nonmetal, they form a bond. Anyone have any idea what this type of bond is called? An ionic bond. I don't know.
So the word that starts with M, I forgot what it's called. It's bigger than atoms and it's combined together.
The molecule,
That's
a
what I think it's
molecular
called.
bond or something? Nope. We call it an ionic bond. When a metal and a non-metal react, they form an ionic bond because one became a positive ion, one became a negative ion, and they stuck together. They attract an ionic bond. Okay, so here we go. And almost 99% of people answer this question wrong. It's okay, we can be friends. If metals lose and non-metals gain, then who shares? Metalloids is wrong. Give me knuckles though, because that's like, it's gotta be. That's the only thing left, right?
They both share when they take and gain.
Okay, well, he didn't get me. He's sort of right. But Daniel, if you give your friend a Christmas present, do you expect them to share it with you equally? Not usually, right? I don't give Derek $50 for Christmas and expect him to give me 25 of it back. That'd be cool. But in this process of ionic, it's a complete giving. They don't share. Okay, so here's what does share. Remember, all atoms want to get 8, and metals can lose. The gases share. Now we're going to be careful. Someone else said gases right here too. Who was that? One of you. And it's Tom Davidson's pet peeve. It's not gases. We call them nonmetals, which are mostly gases. So I know what you mean. But here's what happens. When you share, it's between 2 nonmetals. You with me? Between 2 nonmetals. Because nonmetals want to take. But if you get 2 of them, they both want to take. They're forced to share. They don't want to, but it's their only option. So we have losing, gaining, we have sharing, and we'll call this one. Did I already get yellow? Nope. It's shared between 2 non-metals. They have to share. That's the only way they can both gain is by sharing. You're sort of with me? Okay, so we have a substance here. I'm going to call it water. Uh-oh. What's the formula, excuse me, for water? H2O. Both H and O are what type of atoms? Non-metals. So they are going to react, and the only way they can get happy is to share. There's no losing and gaining in non-metal land. If they can find a metal, then they're going to steal it. And that's why all those metals blew up in water. They don't want to share, but if they only have each other, they have to. So follow my logic here. There's an O, and it's in family 6. So how many dots does it have? 6. 1, 2, 3, 4, 5, 6. Then there's an H, and it's in family 1. So how many dots does it have? It has 1. And then there's another H, and it's in family 1. So it has how many dots? 1. If these guys will share this pair and this pair, then oxygen has a full octet. 2, 4, 6, 8. And hydrogen, and this is what Daniel brought up earlier, hydrogen has a full octet. And I know you're annoyed. Hydrogen only has 2, right? Well, look at the top row of the periodic table. How many elements are in the top row of the periodic table? 2. So really, to get to family 8 or obey the octet rule, hydrogen just needs to gain 1. Are you okay with that? I'll take it. All right, that's a good way to explain it. That violin and I, we're going to meet one day, and my head is going to hit about right here. You're welcome. Yeah, thank you for saving my life. Okay, now look, you've known water was H2O before, right? But now you know why water is H2 to 1O. And that is because in order to satisfy the octet rule, we have to fill one here and one here, and hydrogen only had one to give, so I need two. Who's with me? Cedric.
What about special cases like hydrogen peroxide?
Well, we'll deal with that later. Chemistry is full of exceptions. I showed this meme to my AP Chem kids, and it's like, it shows a book, and then it shows another book. And this is chemistry, and this is chemistry with exceptions. And that's how chemistry really is. It's like, hey, 99% of the time, the world does this, except for these times when it doesn't. And that's like a whole chapter. So H2O2 goes in here. It's not happy. That's why even sunlight causes it to change, because it's very unstable. Hold on, you're after him. Go ahead.
So would hydrogen ever want to lose an electron?
Hydrogen can be forced to lose an electron, but it has to be with something like fluorine, or we have to we have to use energy to do it.
I'm guessing that helium is one of the weird exceptions of a sort, because like normally for the row 8, normally they have 8 or
Right. But helium only has
2.
two.
It's weird.
It is weird. And it's because of quantum mechanics.
Because there's only
Okay.
it's like one
There's-
S2
Yep.
and SP6, but SP does 1P.
There's
does
no
not-
there's no 1P.
doesn't exist.
Right.
1P
Okay. Last question, then we're gonna move on.
It's not going to change the thing.
Okay, last statement.
H2O2 would work if all oxygen shared one and then each hydrogen connected one.
Right.
One
That is, it's 100% true. But oxygen, we're gonna learn a term in a minute called electronegativity. Oxygen is the second biggest bully on the whole periodic table. It does not want to share with itself. So that's why it takes from hydrogen peroxide. That's how it works, but that's why it's unstable, because oxygen is looking for some other partner as fast as it can find one. Last one now, for sure.
So, back to H2O, right?
Okay.
If they're sharing, how can the electron circle if it's still bonded to the oxygen?
Well, that's a good question. And that's a deep question. The answer to that, you may recall, is we don't actually know where electrons are. We don't really know. We know that they live somewhere around here for oxygen, and then somewhere around here for hydrogen. Now, we're going to learn in a second that hydrogen's a lot less electronegative than oxygen. So this green cloud of where we think it's going to be, oh, they're connected. That was stupid. But it's going to move a lot closer to oxygen. And by the way, in biology, you learn two total things. Mitochondria, powerhouse of the cell, check, he passed. And you also learn water is polar. Is he the only one that passed biology?
I did, but I
Okay, well this, okay, so you haven't learned those two things yet, which you probably have. This is why they are. This is why water is polar.
what is for
We're gonna learn. We're gonna learn it. Okay, we're just jumping ahead. You guys have awesome questions. I love them and I appreciate them, but some of them took us in the future. Are we all right with this though? Okay, just one last thing.
H2O.
When two nonmetals are forced to share electrons together, they form a bond, and it has a name. And its name actually makes sense. To me, ionic bonds, that makes sense too. A bond between ions. This one makes sense. It's called a covalent bond. A covalent bond. Good. Think about how it makes sense. Valent means valence electrons. Covalent means they're together. In a covalent bond, they share their valence electrons to satisfy the octet rule. Okay? Metals lose if a non-metal is there to steal. I have no idea where I'm pointing. That was a miracle. All right? But, and they form an ionic bond. But if there's no metal, they have to share. Okay, going back to day number 1, here we go. You're like, just get it. Oh, I'm so bored right now. Well, here we go. What did I say about water and oxygen? These two nonmetals are sharing right now, right? Do they want to? No. So I give them a metal. Does that metal even want its electron? No. Oxygen wants the electron. So what it does, it takes the electron from, I can reach sodium. It takes sodium's electron and it is happier. It still has to share with one H, but not two anymore. And then it kicks the H out, and now the H's have to share with themselves. And they're not very happy about that, but it doesn't matter because in this family, O is the boss, and this arrangement is the happiest. Lithium's pretty excited, oxygen's pretty excited, and life's great. It's all about, in water, they had to share, so they were covalent. I add a metal, they can now form an ionic bond and be a lot more happy. Okay, it's why everything happens in chemistry. I've said too much. Okay, the last thing here. This is kind of cool. I'm going to erase all this. And then this, I'm going to, nope, I didn't mean to do that yet. I want to make a copy of it first. Okay, this is the electron configuration of fluorine. You okay with that? Fluorine is element number 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. It's almost happy. If it would fill that, it'd have an octet, right? 1, 2, 3, 4, 5, 6, 7, 8. It's so close to be happy. So when fluorine is around another fluorine, to be more stable or to be happier, they form what we call a not a polyatomic ion, I'm sorry. They form a diatomic atom. Does that sound familiar to you? I hope so, because they are on your periodic table with little 2's next to them. Good job, Griffiths. Do you see the 2's next to the F? This is why. F is not very happy right now, right? If it can find another F, they will overlap their valence electrons, and now both of them are full. So we do not find just a single F atom when we look out there. It is always diatomic.
You split it.
Can I split it? If I put any metal on the planet, these two will break up as fast as they possibly can to go steel, because they're mad. They do not want to share a car. It's like twins in high school. It's like, no. All right. So they are hunting all the time. If there's no metal out there, they're stuck. But if I add one now, let's just say I add lithium, this reaction will very exothermically happen. It will give off a ton of energy because it will form lithium fluoride. And it forms 2 of them. This is what Roach was talking about before. He had noticed they didn't balance. All right. So that will make both lithiums way happier because they're no longer sharing. They stole. Okay. They only share if they're forced to. But yeah, we can split them by giving it something to steal from. All right. That was fun for me. There's more. Whoa, I feel like that's the same slide. Whoa, I feel like, wow, I've said all this before. Huh. Here's a summary. Covalent, we're going to learn this later, so don't write this down. They're forced to share. Some don't share very well. We call those polar. Some really share, and we call those nonpolar. We'll learn that later. That's kind of out of order. Okay, I said all this as I said all that. So here we go fast. Each noble gas, with the exception of helium, has 8 electrons in its highest energy level. Helium only has 2 because it only needs 2 because it only has an S shell, and S's only hold 2. Next. All right. So there were some dots. Let's just do the dots real fast. So we have H, okay, yellow, that's not gonna work at all. H and put one dot, and then put a plus sign, and put an H and one dot, and then put an O and put 1, 2, 3, 4, 5, 6. And then put your equal sign, and then you have H, 1, 2, 1, 2, 1, 2, 1, 2, H.
I think it already has that.
The dots? On your side, it does not.
So H's and O's, you just have to put a dot in there.
Okay, so you have an H then, put one dot, an H, put one dot, an H, put one dot, an H, put one dot, a C, put 4, and then you get CH4. Good job, that's methane. If you took a shower today and it was warm, high chances that you used this, you lit it on fire, that heated your water, and then you showered in it. This is natural gas. If you have propane, it's different, but whatever. It has 3 C's. Okay, dots good enough? Okay, now let's come here. Electronegativity. What a great word to type out. Electronegativity is the power of an atom to attract electrons to itself when it is bonded to another atom. Okay. When you have two atoms and they are either going to share, lose, or gain, it's dependent on the electronegativity difference between the two atoms. So you have this periodic table right here, or on this side. You okay with that? In the bottom right-hand corner, look at that so I know you're looking. In the bottom right-hand corner for this table, it has these little numbers. Thumbs up. Those are the electronegativity values. You don't have to ever calculate them. You just have to know that silicon has a 1.8. dByte is the name of that unit, but it's just 1.8. That's all you care about. You with me? That number is basically how strong it pulls on electrons when it's bonded to something else. And no surprise, F has the highest value. F has the highest value. Where is the lowest value, if you had to guess without looking? Cesium and francium. So F is high and right, and it's really reactive because it steals. Right, it's the most. Way down here in the bottom left, CS and FR is a 0.7. They hold their electron the weakest. So if you have a high electronegative value, you're really reactive. If you have a low, you're really reactive because you're easy to take from and you're good at stealing. Okay. I don't know. I have like a few seconds. There's the arrows. Now, the other goal for today was to determine the electronegativity difference. And I knew it would be crunch time because I talked too much. That's true. To calculate the difference, you find the values and you subtract the small one from the big one. All right, you guys are great. I appreciate your wonderful faces and attitudes. Whoops, that's not what I wanted to do.